I want to go over some of the stuff from this most recent quiz, which I will get you back tomorrow, but the previous one, just because there was a lot of confusion still in the corrections and a lot of questions that a lot of people got wrong, and I want to make sure that you have this together going forward. If you need to update your review guide or, take notes on a study guide or whatever, feel free to do that. So I'm doing the slightly. First questions that were about the hydrogen emission spectra, okay, or emission spectra in general. So the first question, most people did get right, but I think there's still a little bit of confusion about what's happening, exactly what's happening. So let me one thing to do in honors. There's only watermelon left. Nobody likes watermelon. No, it's going to have to be watermelon because all my cherries are gone. About the energy and the electron transitions. So the electrons are generally going to live in what we call the ground state, which is when we write the electron configuration of an element, we are writing it in the ground state for the purposes of this class. You can also have an excited state, but that's not something that you will be required to do. So what makes an electron move out of the ground state in the first place into a higher energy level? Like it's sitting there, what would make it? Okay, so we're talking about not the loss of an electron, not the ionization, but we'll get to that, but just moving up to a higher energy level. Make sure we went through this. So the electron has to take in energy. So the electron, the lowest energy state, the happiest place for the electron to be is as close to the nucleus as possible. So it's going to, in the ground state, it's going to be in whatever energy level it can be in that is closest to the nucleus. For hydrogen, it's in energy level 1. Okay, it lives in energy level 1 unless energy comes into the atom and unless it absorbs an amount of energy. And that energy can be in the form of light. It can be in the form of electricity, like in the gas tubes that we looked at. It can be in the form of heat in the flame test. Lots of things can excite an electron and move it to a higher energy level. So when it moves to a higher energy level, it is going to take in energy to get up there, just like you have to take in energy in order to climb a mountain, okay? The emission spectrum does not show that. The emission spectrum is release of energy. This would be shown in the absorption spectrum. You would see a line corresponding to the distance in energy from the floor to the first of the stool, okay? And that would be a relatively low amount of energy, okay, and we'll get to the other question in a second. In order to go from the ground state to a higher level, I would have to take in a higher amount of energy, which would correspond to a wavelength of light that would be shorter wavelength, higher frequency, higher energy, right? When I'm in this state already, once the electron has already absorbed energy, it can then fall back down either to the first state, the second energy level, or down to the ground state. So the amount of energy that the movement of the electron is going to determine, of any given electron, is going to determine what light gets absorbed and what light gets released. I could absorb, as a single electron, I could absorb a blue photon of light and go all the way up to from n equals 2 to n equals 6, okay? But then go back down to n equals 5 and not all the way down to the ground state. Okay, so that those transitions can be at any length, any direction, and each size of the transition is going to absorb a different amount of energy to get up there. Okay, and that's shown here. Well, imagine up arrows going from either the ground state or from n equals 2 to n equals 3, 4, 5, etc. That is the absorption of energy. Okay. The emission comes when we drop back down. So if I am in energy level 3 and I drop down to energy level 2, I'm going to release that small packet of energy in the form of a red photon. Okay. So, if I am coming from energy level 6 and I'm coming back down to energy level 2, that is a bigger transition and is going to release more energy. So energy is conserved, right? The electron takes in energy from some source to go further away from the nucleus, because that it doesn't want to be close to the nucleus. The default is to be as close as possible. If it gets excited, it's bouncing off the walls like a kid with a sugar rush after Halloween, and it jumps up to a higher energy level. What?
Kid on a sugar rush after Halloween.
That would be the next thing we're going to talk about, which is ionization. Okay. Yes.
Sorry, what was like the very first part of that sentence? About jumping energy level. If you forgot by now, don't worry.
I'm sorry, I forgot. I got distracted by ADHD.
Your energy jump? Yeah, I was thinking about that. I don't know. I just zoned out for half a second.
Oh, okay.
Don't worry about it.
Okay. So the energy the electron takes in determines where it jumps to, and from a particular starting point that it was already in. Okay, and so if my electron energy level and it drops back down to the second energy level, that is a bigger drop than going from 3 to 2. Okay, and so that is going to release a little bit more energy in the form of blue light. Sorry, I'm terrible at throwing these things. Right. So the release of light is what we see in the emission spectrum. We don't see the absorption part unless we're looking at an absorption spectrum, okay? Which is hard to see. We can't sort of physically do that as far as the stuff in the visible range. So when we look through a spectroscope and we see these lines, we see all of them at once when we're looking through a gas tube, because there are billions of hydrogen atoms in there, all of which have their electron going into slightly different places at different times. Okay, and so we see all of them because it's what we're looking at is the concatenation of all of these transitions, including the ones that we don't see because they're not in the visible range. Okay, so that is what's going on when we look at the emission spectrum. What's happening, what we're seeing is the result of electrons moving to lower energy levels and releasing photons of light. Okay, so they have a certain amount of energy when they're at the higher level. They're wired, they're excited, they just had coffee, whatever, and then the crash comes and they go back down. That energy has to go somewhere, okay? And so that energy goes into the light, okay? Because light is energy. That's what light is. Okay. Okay. This was a very commonly mistaken question, and that's on me. A lot of you put n equals 2 to n equals 1 because, well, there's only a difference of one energy level there. So that's a small transition. But you have to remember that the energy levels get closer together as we go further away from the nucleus, right? That is called convergence, which we will come back to in a second, okay? So the n equals 1 to n equals 2, 2 to 1 transition is going to emit light that is too high energy for us to see, okay? And that's going to be the biggest single level transition, okay? Now, 3 to 1 is going to be bigger than 2 to 1. 4 to 1 is going to be bigger than 2 to 1, okay? But 2 to 1 is going to be bigger than 3 to 2, which is going to be bigger than 4 to 3, which is going to be bigger than 5 to 4, etc. So I don't think I made that clear enough, so I apologize for that. So make sure that this diagram or a circular version of it is firmly lodged either in your head or your notes or in some way that you can come back to next May and say, oh, right, there's that convergence thing. Okay? And in the exam, when this exam was taken, from which this question was taken, that the choice that those of you who got this wrong chose was the most commonly chosen distractor, 2 to 1. Like anyone who didn't get it right pretty much chose that. And it makes sense, but realize that there is that difference in the distances between the energy levels. Which takes us to question 10, which a lot of people unfortunately didn't even bother trying to correct. And I'm sorry if that was if this question was stressful. I will point out that the examiner's report on this says it was probably the most difficult question on the paper, on the entire exam, okay, of that year that this was published, okay? Targeting a very precise piece of knowledge. Only 20% of students could connect ionization energy with the convergence limit of the spectrum. Okay, so that, and the mark scheme has convergence limit in there. That's the key words that you had to say in order to get that point, or in order to get the corrected point. I will try in the future to tell you when I hand back a quiz if we're looking for a very specific phrase to kind of give you that heads up. We did talk about this, and it was in your study guide, but it was this brief little thing. And that, unfortunately, is going to happen on the exam. There's going to be some little thing that you breezed through that I maybe didn't even talk about or barely touched on that you don't have in your notes or your review guide, and you're going to say, what the hell is this? And I'm sorry that it's going to happen, okay? But I wanted to clear this up. So that, let me see if I can find, yeah. So the convergence limit is where we see lines on the spectrum, even the ones that we can't see. You can see these are colored. That's because they're in the visible range. The red and the teal are farther apart than the teal and the violet, and farther apart than the violet and the other violet, if you can see that one. Okay, and that happens at every level in the visible range, in the smaller than visible, less energetic than visible light range, and in the more energetic than visible light range. So we can't use visible spectra or visible light to determine the ionization energy because it's looking over here. Okay, when we see the biggest convergence here, that's the point at which you see how they're all running together to the point where you can't even separate those final lines from each other, okay? That is where the ionization energy, that's where ionization happens, okay? It might be, in some cases, just before the ionization happens, because it's going from 7 to 1 or something like that. But we use that point, that convergence limit, as a way to say this is what the energy would be if we had ionization. So we're looking at the emission spectrum, okay, which is telling us about energy that's released by the electrons when they fall back down. We're using that to calculate how much energy would have to be absorbed to go completely out of the picture and ionize. Okay, so it's that's one of the things that makes this question difficult, is going from thinking about emission spectra to saying we can also use that to calculate how much energy is absorbed by the electron to just completely leave the atom entirely. Okay. So again, I think that's on me for not explaining it well, but it's also a function of the test. And I'm not going to shy away from the tough questions on your quizzes, but I will try to do a better job of, like I said, explaining when there's something that is a particular thing that I'm looking for, and in which study guide would you find it? Something like that, so that you have a little bit more direction and don't feel so lost at sea about, or having to write paragraphs about something that's not related to what the question is actually asking for. So for anybody who put work into trying to explain this and did not get a point back, I'm sorry. I have to do it. I have to be somewhat brutal about this to give you the preparation that you're going to need to understand what. But I will try to be a little bit more. Three. Better.